Welcome to day 2 of our lesson on 1.4, where we're talking about continuity and one-sided limits. Just to recap, in our last video we talked about the definition of continuity, continuity at a single point, continuity on open intervals. We talked about discontinuity and what it means, the difference between removable and non-removable discontinuity. We looked at 4 functions and determined if they were continuous, and if they were not, what type of discontinuity did they have. We looked at some one-sided limits. We looked at what a limit from the right and from the left looks like. We looked at examples where we looked at the limit of a radical and a greatest integer function. We're going to start today by looking at theorem 1.10, which we are going to call the existence of a limit. This theorem states that we're going to let f be a function, and we're going to let c and l be real numbers. Then we can say the limit of f of x as x approaches c is L if and only if 1. The limit of f of x as x approaches c from the left is equal to L, and the limit of f of x as x approaches c from the right is also equal to L. So basically what this says is if we approach f of x, if we approach c from the left and the right and they equal the same thing, then there is a limit. Right now we're going to talk about the definition of continuity on a closed interval. What we say is a function f is continuous on the closed interval from a to b when f is continuous on the open interval from a to b, and when the limit of f of x as x approaches a from the right is equal to f of a, and the limit of f of x as x approaches b from the left is equal to f of b, we can say the function f is continuous from the right at a and continuous from the left at b. So let's look at our next example, which, if we're continuing from our last video, this would be example 4, where we are going to discuss continuity of the following function. And that function is f of x is equal to the square root of 1 minus x squared. What we can say is that the domain of f is the closed interval from -1 to 1, because if we used any numbers that are smaller than -1, like -2, our function would give us an imaginary answer. If we used any numbers bigger than 1, like 2, again we'd get an imaginary number, because 1 minus 2 squared would be 1 minus 4, which is -3. And the square root of a negative number gives us an imaginary answer. If we were to use -1, 0, 1, or any numbers in between -1 and 1, any fractions or decimals, we can get a real answer. We can test it by checking the limits. So if we find the limit of the square root of 1 minus x squared as x approaches -1 from the right, so we're looking at all the numbers that are greater than -1, that limit's going to get closer and closer to 0, which actually is f of -1. And we can also check the limit of our function as x approaches 1 from the left, which again equals 0, which is also our function when f, or when x is 1. So we can conclude that this function is continuous on the closed interval -1 to 1. This is now going to lead us into our next theorem, Theorem 1.11, properties of continuity. We say if b is a real number and f and g are continuous functions at x equals c, then the functions listed below are also continuous at c. So our first case is going to be some scalar multiplication. So if it's a scalar multiple, if we have our b value, which is just a real number, and we multiply one of our functions by it, it's a continuous function. Sums and differences also work. So sum or difference. This pretty much says if we take our two continuous functions and we add or subtract them, we're going to get a continuous function. Products are also going to work. So if we take two continuous functions, f and g, and we multiply them, we'll get a continuous. Lastly, quotients will work. If we take our two functions and we divide them, we'll get a continuous function. However, in this case, there is a constraint. We cannot have g of c equal 0. We, so far, either with myself or your last teacher, have talked about different types of functions, 4 of which, for different types, will always be continuous with values in their domain. And these types of functions are any polynomial, any kind of rational function. And as a quick reminder, a rational function takes 2 functions and divides them. We can have a radical function be continuous, and we can have trig functions be continuous. Let's also talk about theorem 1.12 on continuity and a composite function. This states if G is a continuous or is continuous at C and F is continuous at G of C, then the composite function given by F of G of X, or the fog of X. Is continuous. At C. Let's look at example 6, which we are going to again look at testing for continuity, but of different functions than we looked at before. So the first function we're going to look at is, we'll call this A. F of X is equal to the tangent of X. What we can say as far as this one's continuity is that the tangent function, it is undefined at X equals pi over 2 plus n times pi, where n is an integer. So tangent, remember, is sine over cosine. We would say tangent is undefined whenever cosine's value is 0, and that happens at pi over 2 and any value where we would add pi to that. Other than that particular point, or those points, tangent of X is continuous. So we can say tangent of X is continuous on the open intervals, and I'm going to give a sequence of those. So we've got some that can lead up to it, from negative 3 pi over 2 to negative pi over 2, from negative pi over 2 to pi over 2. These are open intervals, not closed, because we are not including that negative pi over 2, or we're not including any of these values. It's just the values between these that tangent is continuous at. So we also have that from pi over 2 to 3 pi over 2. And if we kept adding or subtracting pi, we'd find more intervals where tangent is continuous. So we're still on example 6. But we'll now call this one part B. We're going to look at the function g of x is equal to the sine of 1 over x when x is not 0, and 0 when x is 0. Recall that the function 1 over x, it's continuous at all values except x can't be 0. At that point it is undefined. And sine is continuous for all values. And because of theorem 112 on composite functions, if we have sine of 1 over x, we can say that it is continuous for all values except x can't be 0. And if we were to find the limit of sine of g of x, it's not going to exist because of that property. But we can say that it is continuous on the open intervals from negative infinity to 0 and from 0 to infinity. We can't call these closed intervals because we're not going to include the actual value 0. And then let's look at our last theorem. We'll call it theorem 1.13, and we're calling this the intermediate value theorem. What this states is if f is continuous, f is a function, on the closed interval from a to b, and f of a cannot equal f of b, and k is any number between f of a and f of b, then there is at least one number, we'll call it c, in the closed interval a to b, such that f of c is equal to k. Let's use this idea in example 7. Where we're going to use the intermediate value theorem to show that this function f of x equals x cubed plus 2x minus 1 has a 0 on the closed interval 0 to 1. Really what we need to show is that f of 0 is going to be smaller than 0, and f of 1 is greater than 0. When we put 0 in, we get 0 cubed plus 2 times 0 minus 1, which is going to equal negative 1. If we put 1 in, we get 1 cubed, 1, plus 2 times 1, 2, minus 1. 1 plus 2 is 3, minus 1 is 2. From that, we can conclude there has to be some value f of c that does equal 0.